Okay, hello everyone. Good evening to all of you. Let us start. So, can you see my screen? Can you please anyone respond? Screen is visible. Can you see the screen? I think so. Okay, we can start. So, this is the second problem solving session for myself, and as I told in the last class also that we'll try to organize the class in such a way that so we'll cover some of the basic ideas. We'll recap some of the things taught in the class so that we can brush up our basics, and then in the second part we'll try to solve, approach to solve some of the questions, right? So let us start. So in this second week actually, so mostly we discussed the isomerism of organic compound. Okay, what are the types of isomerisms? You have constitutional isomerism. Okay, like similar molecular formula, you can have different type of compounds, like you have this butane. Okay, or you can have uh, this branch compound. So this is free chain. and this is branched. Okay, these are called the constitutional isomers. Then you can have,
Sir,
yes.
last week video maybe you are not uploaded. Is it correct?
Yes. I have not uploaded because I need
Is
to
there any
correct
issue?
some
Is
of
there?
I need to correct some of the slides, so that is why I could not, because I was little bit busy last week. So I will do it today. Okay, after this class, I will upload both week.
Uh,
Okay. Yeah,
from
yeah.
last 1 week onwards, I will be wait for the
Oh,
uploaded video.
okay. I will upload it today only. I'll upload it. Okay.
So this week you maybe upload, you need to upload the last week along with this week also.
Yes. Both I will upload today.
Because I have some work. Whenever I free, I will
Sure,
saw
sure,
that
sure,
video.
sure, sure. Don't worry. I will upload it
And
today.
one more small request is there, sir.
Please.
You may completely speak in English, not to any other Hindi. It's my request.
Yes. I try to do that because we have some, regulations to conduct the classes. So I just,
Because we are south down state, that's
uh,
why
yeah.
can't
I can
speak in
understand.
Hindi properly.
I can understand. I can understand.
Uh, so we are comfortable only English.
Yeah, sure. That will not be a problem. Thank you.
Uh, okay, thank you. You carry on.
So first thing is the constitutional isomers, where you can vary between free chain isomer as well as branched isomers. Then you can have configurational. So here you have two actually. One is called configurational, another is called conformational isomers. So both are related, with the arrangement of atoms in space. Okay, this both isomerism are related to the arrangement of atoms in space, but conformational isomers, especially, these are relates with rotation along single bond. Okay, so why single bond? Because you know that if you have a single bond, single bond C, you have a direct overlap, right? Which is more as called sigma bond. Okay, that is direct overlap. And if you rotate this one, suppose you have an axis here, suppose you have an axis. Okay, if you rotate this molecule along this bond, so there is no, change in the energy. So it will not affect on the energy, because this orbital overlap will not change along with the rotation or the angle, right? Because it is a head-on overlap. It is a symmetric overlap. But if you have something R group present here, so I'll just write it R1 R2. Here also you have R1 R2. So then now if you rotate, the position of this R1 R2 groups will change in space. So there will be different kind of interaction between them. So that is why this conformational isomer, this term come. Okay, and configuration is related with only one carbon center. Okay, like you have must have heard of this, RS configuration. Okay, this we'll study later. So this actually helps you, to determine chiral or optical properties. Okay, so these are associated with configurational isomers, but conformation associates with the rotation along single bond. Okay, and apart from that, you have another, stereoisomers. Then you have geometrical isomers. So whenever you can see there is a, restriction of rotation. So restriction of rotation. Suppose in case of sp2, so you have c double bond c, so you have different groups here, okay, and you have different groups. So based on the position of your atoms, either they are cis or trans, you can have geometrical isomerism, right? And stereo isomers is also associated with your configuration, and especially optical isomers. Okay, this we can study later. So, so in this particular class, what we intend to define the conformational isomers of alkane. Okay, mostly it is associated with alkane because alkanes are only having single bonds. They don't have any double bond. They are saturated. Okay, so that is why this conformation term only goes with the alkane, and obviously cycloalkanes. Why are they important? Important because of controlling the reactivity of the compounds. So let's say for an example, uh, you have this cyclohexane and you have two substituent here with and something X. So I'll consider it as bromine. So now, as a simple, epoxidation reaction, what it can do? So it has lone pair, so it can attack in this position because it is an electronegative group. So you have delta negative here. Here you have delta positive. So your electron density can attack here, and it can take away this bromide. Huh? So you can form this kind of compound. It is called epoxy compound. But the situation is not as simple as it is looking here. Okay, so you have to go to the 3D representation. So how will you represent? So I'll discuss it later, but first let me go with this example. So this is a typical cyclohexane that looks in 3D. Okay, and then you have your OH here, you have the lone pair, and you should have your X exactly opposite, so that you have your orbital, bonding orbital through the CX bond, and anti-bonding orbital on the other side. So then what will happen? Your electron density will attack to the anti-bonding orbital, and now when they are pushing the electron to the anti-bonding, so this one will get intensified and this one will leave. So now you can have so something like that you can form. Okay, so this will not be properly on the top side, so it will be something like this. So this also depends on the uh, stability of the particular structure. So this all depends on the energy associated with the system. So let us assume that it was not this way. Like you have this OH here, but you don't have the other bond exactly opposite, so it is like this. Okay, then your bonding is here, anti-bonding is here, so your lone pair has not any access to attack to the anti-bonding orbital, so this reaction will not favor. Okay, so this one, if you convert to 2D, it will look like this. So I will discuss it in detail. So in this position, if it is in the top side, okay, so these three are in the top side, These three carbon atoms are on the downside. I may depict with another color. This one. So these are on the downside. These three are on the top side. So now oxygen is on the axial position. Okay, you can write it like this, which, and you have just adjacent carbon. You have this bromide or halide, anything. So this is exactly opposite. So this is the downside of paper. So this should be your representation. In this case, if you represent it in 2D, then it will look like this. So similarly, oxygen is in the top, and then on the adjacent, okay, this is also in the top. So I'll discuss one more time that how you can without any mistake can convert 3D into 2D or 2D into 3D for the cyclohexane. We'll come into that. So now, uh, so let us start with constitutional isomer. Okay. So how you can represent a hydrocarbon? Hydrocarbon mainly based on carbon and hydrogen. Okay, these two are the main component. Now let's say you want to draw this one. So that is a propane molecule. So propane looks like CH3, CH2, CH3. So what is the Lewis structure or Lewis diagram? It should be like this. So this is purely a 2D representation. Okay, you don't have any 3D idea from this how the molecule look like. So this is the name of the representation. Okay, how we represent in 3D. So this will look like something like this. Okay, so you have one CH3 here. In the middle you have methylene group CH2, and in the end you will again have CH3. Okay. Now for alkanes, general formula to represent the compound is CnH2n plus 2, right? We all know this from our basic idea about organic chemistry. Then uh, so if you have this, what is this one? 1, 2, 3, 4, 5. Okay, this is called pentane, but this has many isomers. So this will is called N-pentane. So whenever you can see, you have a linear chain. So this one is called N-butane. Okay, so this one is called N-pentane, like that. Okay, but with this same formula. So what is the formula here? So you have C5 and 3, 2, 5. So 2, 2, 2 is 6 and 6. C5H12. That means it is matching with this formula. C5 and H10 plus 2, that is 12. So with this same formula, you can have this one also. Okay, see, 1, 2, 3, 4, and 5. Okay, so this is also having C5H12 formula, and this is called isopentane. Okay, then if you have something like this, 1, 2, 3, 4, and 5, this is called neopentane. So these are all called constitutional isomers. Another example, you have this butyl groups. So you have something, CH3, you start from here, then CH2, CH2, and this one also CH2, and you have a open chain, so that can be connected to the other part of the compound. Okay, so this group is called N-butyl. Then you have If you have something like this, you have the other part. So this is called sec butyl. Okay, and you have this one. One, two, three, four. So if you have this one, this is called isobutyl. Okay, like that. So these are all positional or constitutional isomers. Then you can go to the next part. So one thing to remember is that the more number of carbon atoms in chain, okay, more constitutional isomers. Why? Because you will have much more probability of branching the chains. Okay, you can have different combination of chains. So that is why more number of carbon atoms in chain, more number of constitutional isomers. So if you go starting from butane, pentane, hexane along to 17, 18 long chains, so there will be much more possibility of getting much new structures. So that is why organic chemistry is expanding day by day. You can you know basically you can synthesize different kind of new molecules. Okay, you have a lot of probability to get new molecules. So that's one part. Now, so we have a classification of carbon atoms in compound based on their connectivity. What connectivity? Connectivity to another carbon atoms. Say you have you know CH3 that is connected to another CH2, then it will go on and on. Okay, so I will just write it as R. So this carbon is connected to only one carbon. So this we represent as 1 degree or primary carbon. Suppose you have this compound. You have one carbon here. So now you can see it is connected to two carbon. It is called 2 degree. 2 degree or secondary. Similarly, you have another carbon here which is connected to three carbons. So this is actually called 3 degree or tertiary. Okay, and then uh, based on this you have naming protocols for organic compounds that we already know, I think. So I will not get into this one. So this is called a IUPAC, International Union for I think Pure and Applied Chemistry. So IUPAC nomenclature is the basic idea. So I will not go into this. Then I will move to conformational isomerism. So I told you if you want to study reaction dynamics in organic chemistry or basically try to understand any reaction mechanism, you have to have the basic knowledge of what is happening in the molecule. So you need to have you have to have some knowledge about the reactivity, some steric, some conformation of the molecule. So all this thing, the idea is required to understand the mechanism of any reaction. So that's what we'll start with some basic phenomena. So as I told you that this conformational isomerism relates with bond rotation, okay, sigma only. Then Uh, so it is also related with the energy that is stored in the system. Conserved energy within the system. I'll discuss it. Okay, then you can have an understanding what does it mean. And then for any stable, conformer. So this isomer is represented by conformer. Okay, conformational isomer mean conformer. Stable isomer, conformer, strain, okay, as well as energy should be minimum. Okay, so just for your example, I will draw this one. So there are some projection technique, okay, for 3D presentation. Okay, mostly we use Newman projection. What is Newman projection? Let's say you have just with the simple. So you have CH3, CH3. You have ethane molecule. Hmm? Then you can view along this bond axis. Okay, you can view through this, and it will appear like this. You have a carbon atom. You have three hydrogen. Okay, and you have another carbon atom on the backside, but it is you cannot see it because it is already shaded by the front molecule, right? So I'll just represent with another color. So this is the proton of the that is connected with the backside carbon atom, okay, which is shaded by the front one. You cannot see it. Okay, so you are just seeing through this bond. It's called Newman projection, and same thing you can show in another way, that is called Shawhorse projection. Okay, so you can represent this same molecule in another way. Suppose this is your C1, C1 and C2. So this is your C1, and then you have C2. Okay, so you are just rotating that one, and you try to view through another angle. This is called Sawhorse notation. That is called the earlier one is Newman projection. Okay. So this will help us to draw the conformer of different molecules. So now with the same example, let us go forward to understand some of the things. So what I told you, in an ethane molecule you have two carbon. In this case, I just uh, shifted these hydrogen atoms a little bit, but these are actually eclipsed. Okay, so eclipse means this front hydrogen will fully shade the backside hydrogen. Just for representation, I am showing like this. So there is the angle between. So this angle between is called dihedral angle. So this one hydrogen, then one carbon, okay, then another one carbon, and this hydrogen. So you have a angle between this. So this angle is called dihedral angle. Can you follow it? So dihedral angle, it uh, relates to torsion and strain in the molecule. So in this case, you have dihedral angle 0. Okay. So now just let me rotate the other one, rotate this bond 60 degree. So what will happen? The front atom is same, hydrogen will be at the same position. I'll just rotate this bond to like this. Now what you can see, this angle has changed. Okay, this is now 60 degree. So dihedral angle has been changed. So there will be change in the uh, interaction. So suppose we are, preliminary we are doing with hydrogen. Let us assume you have bulky R group. Okay, bulky R group means you have something like this. This group you have this group. So these are very bulky, right? So if they are standing, or if they are on the adjacent carbon atoms, there will be lot of collision in between them, right? They have lot of steric hindrance. So this angle will not be preferred because of the high strain. Okay, compared to this one, if their angle is reduced, sorry, increased, the dihedral angle, so their steric repulsion will be less. So energy will be less. Okay, so this one will be more favorable. Okay, so just for ethane, if you try to correlate your energy of the system. So suppose this is my energy axis, which is y, and x-axis I have dihedral angle. Yeah, dihedral angle, and you have different angles starting from 0. Then you have 60, 120, 180, 240, 300, all the way up to 360. Okay, and then uh, I can virtually set an energy. So this is my maximum energy. This is my minimum energy. Minimum energy is what? For the stable configuration, which is this one. So I forgot to tell you. So this has a name. This is called when the dihedral angle is 0. This is called eclipsed. You already know of this term. I just giving a recap. And this is called staggered. Sorry, not Koch. It's called staggered. So this is called eclipse. This is called staggered. So now I can draw a virtual energy line. The energy maxima. This is energy minima. So at 0 degree you can see it is unstable because of high energy. So it will be at this position. Then at 60 it will be at this position. If you one more 60 degree you rotate it, then it will be exactly same as 0 degree condition. So it will again be at high energy. 180 it will be at low, 240 high, 300 low, 360 high. So how the energy plot will look like? Something like this. Okay, this is a pretty basic scenario. Okay, so whenever you are introducing some large group, okay, on this carbon, so things will change because they have their own interactions. So I'll discuss it. So what is the reason? So people want to study what is the reason behind this change in energy when they will go from one angle to another angle. So initially what was proposed reason was two. So one, they proposed that repulsion between hydrogen atom, and similarly repulsion between electron density. From where electron density is coming? From the bond. Okay, you have CH bond, so there you have some electron, right? It has some orbital, so this have some electron density. So the repulsion between the electron density. So this was proposed but not proved altogether. What was proved from some uh, theoretical calculation, theoretical calculation, sorry, proved involvement of molecular orbitals. How? That we'll discuss. So suppose you have this structure. So you have two extreme. This is your staggered, and you have your eclipsed. Now I will represent this one in Sahor's form. Okay. Now what can you see here? You have this hydrogen all over. So for this hydrogen single bond, you have your bonding orbital here and anti-bonding orbital here. For this one also you have bonding orbital here, anti-bonding orbital here. So only if you are in the exact opposite position, you can have some of the interaction between this. So this will give you some stability. Stability arises. In this position, let me draw it. Both are same, right? So in this case, there will be repulsion. Okay, I need to show the positive and negative sign also. So this anti-bonding, this is bonding. So bonding is generally shown by okay some positive and negative. So this is you know if you have any wave function, you have one positive, you have one negative. So this is the node at zero. Okay, so this is positive, this is negative, this is negative, this is positive. That is why they have some attractive interaction. But here all they have same phase. Okay, this is called phase actually, phase of a wave function. Hmm. So here it doesn't have this much interaction. Okay, this is not possible because they are same phase. So same phase repel, opposite phase are there, then it can interact like that. So this is something that was proposed by theoretical calculation that in the staggered form, okay, there is increased interaction between the bonding and anti-bonding orbitals that gives some stability into the system. Okay, that is why it was less in energy compared to eclipse, and it was most favored form. So this was the preliminary idea where we don't have any big substituent on the carbon center. So let us now complicate the system. We started with the basic. Now we'll go to little bit complicated system. In that case, suppose you have butane. Okay, so butane you can represent like CH3, CH2, CH2, CH3, right? Four carbon you have. So this one you can represent as carbon, then CH3. This is also you can consider as Sohor's notation. I guess you have the idea already that this solid lines, okay, solid lines, these are up of the plane or up from the plane of paper, and this dotted line or dashed line they are below the plane of paper. Okay, that's how we represent this same structure. If you convert to Newman projection, what will it be like? So you have CH3. So just try to see from here. Okay, so CH3 will be on the right side. Yes, and on the top and left side you have proton. You draw the atom here. Now these are eclipsed, so it will come in the same place, right? Now you rotate it. So this is the eclipsed form. So this angle is 0 degree. Now you rotate it 60 degree. What should happen? So I will not change the front atom. It will be like same CH3H CH. So now if you rotate it, it should be like this CH3H H. Okay. Now this angle is 60 degree. Now again we should rotate it another 60 degree. Let's see. So anyway, my front carbon is not changing. It will be like same. So now you can see these are eclipsed now. Okay, but the angle between two CH3 group is changing. Hmm. Now again rotate another 60 degree. So this is 0. Hmm. Altogether. This is altogether 120. Sorry, 0. This is 60. This is 120. This will be 180. Let me finish it. I'll write Me instead of CH3. Okay, methyl group. Now if you rotate 160 again, it will come at this position. Okay, so now if you rotate it one more time, then the methyl will go to here. Okay, so it will be similar like this. It will go to this one if you rotate it one more time 60 degree. So this will be your 240 degree also. If you rotate it one more time from here, then it will go to here. So this will be your 300 degree. And from here if you rotate it once more, then we will exactly end up in the starting position. Okay, so this will be your 360 also. So 360 0 you have 1, 180 you have 1, 120 and 240 you have 1, and 60 and 300 you have 1. Now you have to look for the energy, the relative energy. So how many sets you have? 4 set you have. Okay, now check it. In the starting position you have this CH3 group. Okay, they are big groups, so they are much more statically hindered. Their energy is much more. So this one is
सोता जाओ अरे नींद लगी तो कौन नहीं सुनना हाँ दिमाग को शांत रखने का
most
क्या सोच
energy.
हट इधर
Can somebody mute their mic? Someone mic is open. Okay, so this one will be of most energy. Okay, because these two methyl are in the same position. Now let us search for the other one. 60. What is happening? So okay, this 60 you have these two.
अरे मैं सोच रही थी
Can somebody mute their mic? Whose mic is on? Ikra, can you mute your mic? Hello? Ikra, can you mute your mic? Okay, thank you. So you can see that 0 and 360 will be of the most energy. Then when you compare between these two, like 60 and 120, so 120 you can see this methyl are also eclipsed with the hydrogen. So whenever there is eclipse conformation, it is much more energy than the staggered conformation. So this one is having less than this one, so you can just plot it and then I can show you. So this will be your 0, 60, 120, 180, 240, 300, and 360. And let me give some maximum and minimum. This is your energy. This is maximum. This is minimum. We'll give a indication for a bar. So you know that 0 and 60 you have the maximum. Hmm. So let us just mark it 0 and 360 you have maximum. So just check this one. So here nothing is eclipsed in the 180-degree structure, okay, and methyl are farthest from their position. They are exactly opposite. So this will be least energy or most stable. So this will be having the least energy. Now apart from these three, you can check in this conformation the methyl are far apart, but they are eclipsed with the hydrogen. So there will be some effect of methyl and hydrogen eclipse. Okay, so this one will be more energy, okay, than this one, because here you can see all are staggered conformation. So now you have different type of staggered. Okay, so uh, this is called full staggered when your methyl are in the complete anti. Full staggered. This one can be called as Gauch, Gauch staggered. This one is fully eclipsed. This is partially eclipsed. So this one will have in medium something like here 120.
Good evening, sir.
Yeah, tell me.
Sir, can you explain in Hindi?
No, 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 it's not possible because we have been directed to teach in English only because there are other participants, they will not understand Hindi.
Okay, sir.
Yeah. If you have anything problem, you can just stop and ask me. I'll tell you. Okay. Now you can check this 120 and 240-degree. So these are partially eclipsed. So they are having much energy than the gauge. So gauge is at 60 and 300. 60 and 300. So it will be something like this. The plot will be like, okay, so it will come through this. So the energy curve will be like this. It depends on the interaction between the substituents on the adjacent carbon. Okay, so now uh, how can you track this? How to how to determine or track the conformation? So you can see, so it is a energy axis. So all of these structures having a definite energy. So this is the least energy, this is the maximum energy. But you have an energy gap between them. It's called delta E, energy gap. Okay. So you can see between the most energetic form and the least energy form, you have maximum delta E, maximum change of energy. But if you consider this one, this is not that much, even this is very less. So what happened in room temperature? there is always chance of conformational exchange. What is conformational exchange? You can see you have this axial, this is called axial position, this is called equatorial position. So axial and equatorial position can interconvert. It is just a simple rotation of bond, right? It is just a simple rotation, and this barrier of rotation, this energy gap is not so high, it is very less. So even at room temperature, they can convert frequently. Okay, so you cannot determine them. So in order to determine, we have to go to low temperature. Boltzmann distribution. So you have a thermal energy that is kBT. Kb is your Boltzmann constant, right? So if you decrease the temperature, your overall energy will go down. So your molecule will not have enough energy to go from this state to the higher energy state. It will not have the enough energy. So you can, you know, freeze this state, and you can get information. Because if you do NMR, you know about NMR. I guess you all have heard about NMR. So NMR determines the chemical shift of nuclei. Hmm. It can be 1H, 13C, 11B, anything. Hmm. So this gives the chemical information like chemical environment, coupling, etc. This information is given by NMR. So axial and equatorial, okay, groups behave different. So at low temperature, if you do NMR, you could separate this axial and equatorial proton or any other group that is present there. By this way, you can track, okay, these conformational changes. Okay, then okay. Now we move much more forward. So we'll start cycloalkane. So we are going to the advanced topic. So cycloalkane, as you know, it can be different number. So number of carbon can be 3, 4, and so on. Because by 2 you cannot make any cycle, right? Minimum you need 3 carbon. You can start from cyclopropane, cyclobutane, cyclopentane, sorry, cyclopentane, then cyclohexane, hmm, then heptane, okay, and so on and so forth. You can go all the way. Now you have to check. So how it look like for the cyclopentane? You have 3 carbon atom at the vertex of a triangle, and you have these protons associated with the carbon. So these are called exocyclic protons. This is, outside the ring, outside the periphery. This is called exocyclic. Okay, and Can you let me know what is the bond angle? What can be the bond angle between uh, three carbon? Do you have any idea? So this is around 60 degree. But we know we are dealing with alkane. Alkane means sp3. sp3 should be okay like this 109. So you can see how much deviation is there from the ideal value. This is ideal. Okay, how much deviation is there? So that gives to ring strain or angular strain. So what we have previously known, there are two type of strain. Okay, one is called torsional strain. This I have discussed when we studied this dihedral angle, and this is called angular strain. There are two terms. Now you see that the original angle is 60 degree. So how can it survive? Okay, why it is not breaking? Hmm. So that is why it has some changes in the structure. So let's say we have carbon, carbon, and carbon. So what it should be like, a direct overlap will be like this. This is much more expected. Okay, and then you have this hydrogen, 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 and hydrogen, right? But this is not the actual case. So if you had the direct overlap, then it should have been linear almost, but it is not linear. So this is not true. The actual system looks like something like this. This is the overlap. It is not linear, and these are called banana bond. Okay, because it is bent in space. And what does it mean? Overlap is less. And one more thing is that if you have proper overlap, okay, there will be more S character. But where you have this bent, less overlap, then you have less S character. And where this extra S character goes in the CH bond. So in this bond, in this bond, this overlap is there. So here comes the extra S character. That is why if you can see this bond are not stable. So this is very reactive. This is the reason. Okay, because it wants to lose the ring strain. Okay, so similarly, if you go to higher analog, that means cyclobutane, it looks like this. So you have 90 degree. So we have some deviation from ideal 109 degree, but that is less compared to cyclopropane. And to to reduce angle strain, sorry, not angle strain, torsional strain, and the structure adopts bending, how they are bent. So there are two conformers, either this way. Okay, here we have 4 carbon, or this way. Okay, so if they bend like this, so now this angle change little bit, so it goes to 80 degree. You can see the deviation is much more, angle strain is more, but the torsional strain gets reduced. So that is how it is get compensated. Let us discuss about cyclopentane. So the general representation is like this. You have 108 degree. This is almost same with the ideal case, right? But still, to reduce the torsional strain, it goes through something like this. Okay, so this is how you represent the 5-membered ring in 3D. This is the least energy structure, stable structure. So you can see here that 4 carbon atoms are in the same plane. One is in the top. Okay, here one is in the down, and 4 in the same plane. So what happens in room temperature? This carbon shifts actually. So sometimes this carbon will go to top, sometimes this will go to top, other 4 will stay in the ground. So it will shift, or shuffle, shuffling at room temperature. So with that, we go to the ultimate cyclohexane. This will be much more special because we deal with cyclohexane much more whenever we are considering the cycloalkanes, any cycloalkanes. So n equal to 6, carbon 6 is the most discussed one. So basic structure is like this. You have a hexagon. This angle is 120 degree. It is much more relaxed. But how does it stay in the 3D? So it is something like this. So this is called chair conformer. This is the most stable conformer of the cyclohexane. Okay, you can have either this way or the other way. Okay, it is just if I flip it, it will go to this way. Now this can interchange between. I can flip it this way. It can go to here. Then you will get the reverse. This is called chair conformer. You have another conformer also, which is called half chair. So this is something like this. Okay, this is called half chair. And you have boat conformation. This is called boat conformation. And all these structures you can uh, view through the Newman projection also. So we'll come into that. Okay, so let me just draw once. So suppose you have normal cyclohexane. So how should I represent this one? Let me first draw it. So you have one, two, three carbon on the top of the plane, and 3 carbon on the below the plane. Now I'll name it first. 1, 2, 3, 4, 5, and 6. Now let me draw the hydrogen. In this position, this is called the top part or axial part. This is called the equatorial part. If you go to the below of the plane, this side, so this one will be your top, this will be your down. This on the top, so this will be similar to 1, this will be your top, and this will be your down. This is similar to 2, so same thing. This will be your top, this will be your down. So you can do like this way. Okay, you can understand it, right? So now I'll move this one. I'll move it to new and projection. So how should I view? Okay, how should I consider it? So I will look from here. I will look from here. This is my axis. This is my axis. This is my axis. So this is one atom that I can see. This is one atom I can see. I can see these two also, but I don't see the other two. These are blocked by the front. So how should I draw it? So let me first draw these two atoms. Okay, let me draw the proton. Now you can see one carbon is breached here. So this one I can join it. This is the carbon. I will not show the hydrogen here. Then the other one will be like this. Okay, it's simple, right? And then you have another two proton. Okay, this is how you can represent the cyclohexane. Now let me draw the energy diagram. Okay, this is your E. So similarly, I'll start not from 0. So here it doesn't have a mini 0. So you can just uh, compare between the different conformers. So it should be like this. Okay, so these two are on the same plane. These two are on the same plane. This is the minimum, and this is the chair form. Okay. Now this is what? This is the next higher point. This is the half chair form. Okay. This will be also same. Then you have 3 point. This is the boat. This is the boat form, and these two are twisted boat. This one and this one. So this is more like an intermediate when you are converting the half chair to the boat form. These are more like an intermediate. So you have this structure for boat. So when these two are exactly not parallel, there are some changes in the angle. Much more like an intermediate. So like this. Okay. So there are some changes in the angles in between. So that is called twisted boat. But this has less energy than the boat conformer. But most stable will be the this one chair conformation. Okay. So with that, we move forward. So let us try try to draw the conformers. Suppose we have this one. I have the 2D representation, one methyl and one chloride, and another isomer I will write, one methyl, and this one is the opposite side. So what is the name for this one? This will be, if you number it, if you give the number 1, 2, 3, 4, 5, 6. So that is, these are on the same side, top of the plane. So this is cis. Uh, okay, this should be on the other side, but anyway, I can write it. 1 methyl, 3 chloro, cyclohexane. So this is cis. How should you represent it? Let me first draw this one, and then I give the number 1, 2, 3, 4, 5, and 6. Now, in one position, this is on the top. So I have already told you that you have 3 on the top of the plane and 3 you have below the plane. So for the atoms that are in the top of the plane, so this below top of the plane means here, okay, and here you have hydrogen. This is your methyl. So now 1, 2, 3, third position here. So it is on the same side, means the chlorine will also be this side, okay, and here will be your hydrogen. But is this conformation is the stable conformation? No, because this methyl will have some interaction with this one. Okay. Also, you have some hydrogen here, so this will also have some interaction. So the if you can flip it, so just flip it, then it will look like, so this one will go here. See, now it has been on the top. Here also it has been on the top, but it is equatorial. Okay, equatorial top. So you have to uh, know the relation between this axial equatorial and the top down, how to assign it. And then 1, 2, 3. Okay, then 1, 2, 3 here. Now it is on the top, so it will go to the top, Cl, and here will be your H. Now you can see you have much less steric repulsion. So this will be your correct structure. Okay, now try to do this one also. So let me first draw it like this. One position you have methyl on the top, then this is your methyl. 1, 2, 3. So now chlorine is on the downside. So it will be like this. Okay. If you flip it, then it will be like this methyl, and then chlorine is on the downside, so it will be like this. Now to know that which structure is stable out of these two, you need to consider this interaction. Okay, this case you have here and here. You need to consider this interaction. So you have a reference. I think you can go by the course material. So there you have a reference that how to calculate. There is a value for each interaction. Hydrogen, hydrogen, methyl hydrogen, okay, or any halide with hydrogen. So you can compare to that value, and then you can understand which one will be most stable. Okay, like this. Let us move forward. This interaction is called 1,3 diaxial interactions. Okay, so this is different. So if you have, you know, if you had methyl here, so that will be much more methyl methyl. So this is basically a steric repulsion. Okay, so for the actual quantitative part, you can refer to the course material where the value is given. Then you can calculate by yourself. Now, uh, there is a calculative part. So suppose you have this compound. This is methyl substituted cyclohexane. Okay, but as I already told you, it will have some interaction with the proton. That is called these diaxial interactions. Now, if you just flip the ring, then it will be like this, and your methyl will come here. Now you can see you don't have any interaction. So either you have some hydrogen in that side, but you have 60-degree dihedral angle. So there is no concern for that one. So now you have to calculate the stability. So which one of the conformer will be stable at room temperature. So you have a equilibrium running between these two conformer. Okay, and the rate constant is proportional to product concentration and reactant concentration, and you can calculate this delta G, that is your free energy for the change, is minus RT ln K equilibrium. Now if you are given all the values, so suppose this CH3 H13 diaxial interaction, so this has the value of 1.8 kilocalorie per mole. Okay, so now if you are going from the axial to the equatorial position, so actually you are removing the interaction. That means you are getting stable. Okay, so in this case you have plus 1.8 energy and 1.8 kilocalorie per mole, and here you have 0. So if you go from here to here, you will lose energy, right? So you will have minus 1.8 because you are losing the energy. There is no interaction. There is no energy is getting reduced, right? So your delta G value will be minus 1.8 kilocalorie per mole. So suppose you are having this one at room temperature, that is 25 degrees C or 298 Kelvin, and R value is 1.987 calorie per mole per Kelvin. Okay, so if you convert it to kilocalorie, then it will be 0.001987 kilocalorie per mole per Kelvin. So let me do the calculation in the next page. So delta G equal to minus RT ln K. Delta G is minus 1.8, right? Then you have minus R is 0.001987 as far as I remember, yes. Then temperature is 298 into ln K. So now you uh, calculate it, so you will get equilibrium constant is 20.69, and as I told you, this is relates with the product and reactant ratio. Hmm. So now you can see your product, so you can consider it as 20 is to 1 almost. Hmm. So you can see your product is much more stable. This product is much more stable than your reactant or the axial. So that is why you can calculate this difference. Also, you can know from this delta G value only. You see it is negative, so that is spontaneous. Just simply looking at the delta G value, the sign of delta G, you can just determine the reaction is spontaneous. That means it is going to the lower energy side. Okay. So now let us move. This is okay. So there are some physical properties that are related. Physical properties of alkane structures. So you have different types of intermolecular forces. Between molecules. What are them? Let me list out. So ion-ion interaction. What is the energy value? This is more than 100 kilocalorie per mole. Then you have ion dipole. It's 20 to 100 kilocalorie per mole. So ion you can observe in NaCl, something like that. Okay, and ion dipole also you can observe in some of the ionic solid. And then you have dipole, that is 1 to 10 kilocalorie per mole. Okay, you can observe this dipole in polar compound. Also you can have dipole induced dipole, 1 kilocalorie per mole. So these you can observe between polar or non-polar compound. And then you have induced dipole, or it is basically called as van der Waal, and that is very less, that is physical interaction, and this is general between atom or molecule. Okay, so trend of boiling point. Now with increase in chain number, boiling point increases or decreases? What should be? Boiling point increases, right? Because of the intermolecular forces. So if you see n equal to 1 to 4, you have methane, ethane, propane, and butane. Okay, all are gases, right? But if you go beyond that, from pentane, hexane, heptane, so on and so forth, it will all be liquid. Even you will have some branching. So if you have some branched hydrocarbon, they will have very dense liquid form, due to their intermolecular force of interaction. Now, general thing what we can see, with increase in branching, boiling point decreases. Okay, why? Because suppose you compare between this one, so 1 2 3 4 5 6, it's a n hexane. So now if you increase the branching, okay, 1 2 3 4 5 6, so this is a little bit more, sorry. So if you try to increase the branching, then what we can see, this size, the overall size, it gets shrink, it gets compact. Okay, it is getting much more compact. Then what is the effect? Surface area decreases. Now, as surface area decreases, their intermolecular force of attraction decreases. So less boiling point. Okay. Now let us discuss something about chemical reactivity of alkanes. So basic reactivity of alkanes, so that is the oxidation property. Okay, or you can term it as combustion, because we basically oxidize it. So this is a basic uh, molecule, that is methane. When in combustion, we oxidize it to carbon dioxide, and then we produce water. What is the delay of the reaction? Enthalpy change is minus 212 kilocalorie per mole. This is a pretty preliminary thing where we use methane. So if you increase the chain, then what will happen? Your delta H, the enthalpy, will have some effect. So what is generally observed that if branching is more, then, then what happens? Compound is more stable because it is compact, right? Now, if you try to oxidize it, then the energy released. So this also relates with the enthalpy. So energy released will be small. So how can I show this? So say something you have like this. Okay, this is your primary. So this is your reactant. This is your product. Okay, this is your energy axis. This is reaction coordinate. Now, if you have something like here, okay, which is coming to this. So what is the energy difference you have? Here you have much more energy density compared to this one. So now you can think of, this is your normal chain, okay, P chain, This is your branch molecule. So you can see that it is already stable, okay, lower in energy. So energy loss or energy released from the reaction will be much less, like that. So we'll discuss some more things and then we'll go to the question. Uh, so last part was nomenclature. I think I don't need to discuss it in detail because it is already known. Okay. So for alkane you need to add suffix, to add the suffix in at the end. Hmm. Then if you have uh, some chain like this, CH3, CH2, 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 CH3, this is the branch, and then you have another CH3. So what you need to do, you need to find the longest chain, right? So let me do it in two ways. 1, 2, 3, 4, 5. This is one, and if I start it from another way, 1, 2, 3, 4, 5, 6. See, we can have six carbons in a chain. Okay, with a substituent at 3 position. So what we need to keep in mind that we need the maximum number of maximum carbon atoms in the chain. Then what we need to do, then you need to number from that side where the substituent will come first. Okay, suppose you have something like this. Okay, now I have one here and then one I have here. Now if I number it from that side, 1, 2, 3, 4, 5, it is not correct because this first substitution is coming at 3 position. This is not correct. Numbering wrong. If I do it in other way, so CH3, CH2, CH, CH3, CH, CH3, CH3. So if I do it in other way, I start from here, 1, 2, 3, 4, 5. So this is the right way because my CH3 is coming on the second position. So this is right numbering. Okay, so you need to do this one, proper numbering of carbon atom, and then if you have more than two groups, like you have ethyl or chloro or methyl. So this time you need to consider the alphabetical terms. So it starts with E, C, and M. So C will come first, then will come E, and at the end M. So this is the way you have to put the substitution. So for this compound, what should be the name? So 1, 2, 3, 4, 5, 6. That is hexane, and at 3 position you have methyl. So 3 methyl hexane. It should be one single word, 3-methyl hexane, like that. And yeah, let me uh, discuss something about cyclohexane naming. Cyclohexane nomenclature. So if you have like this, so wherever your substituent is, you start from there. So that is your 1, 2, 3, 4, 5, 6. So this will be termed as 1-methyl cyclohexane. But same thing, if you have something else, so the same compound I will write. Here you have CH2, 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 3, 4, 5, CH2 and CH3. So you can see you have 7 carbon atom here. Here you have 6. So you will not uh, put this one as substitution. So then the cyclohexyl part will be a substitution. So in this case, the naming will be like 1 cyclohexyl, okay, heptane. You should always check that where your large number of carbon is present in the substitute or in the cyclic part. And then just one more slide. So if you have something which is called bicyclo, sorry, yeah, bicyclo compound. What are bicyclo compound? So you have, maybe you have something like this. Okay, there are 2 cycles present, something like this, or something like this. This is called a bridge, and this carbon is called a bridgehead. But in these 2 structure, there are no bridgehead. Okay, so how do you name it? So you need to take care of this both side, 1, 2, 1, 2. Okay, and then you should write like bicyclo, then put a third bracket. So first write on either side of the bridgehead how many carbon atoms are there. 2, 2, and 2 dot 2. Okay, then how many bridgehead you have atoms? 1, and then you count the total number of carbon atoms: 1, 2, 3, 4, 5, 6, 7. So this is heptane. In this case, you don't have any bridge, so you need not to consider the bridge here, but other things will be same. See here, you can see on either side you have similar number of carbon atoms, so it will be bicyclo 2, 2. You don't have any atoms, so 0. Then 1, 2, 3, 4, 5, 6 hexane. What will be this one? Bicyclo, right? 2, 4, 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, 8 means octane. Okay, you understand? This is the way you should do it. Now let us do some question practice. So this is from the practice set, I guess. Yes. So can you try to do it, or you have already done? Can you let me know the answer? So in this case, all the values have been given. In your exam also, it will come like this. So you can see from axial to equatorial when you are going, so your values are changing. Okay. Now you need to consider that it is going from axial to equatorial or equatorial to axial. Now for CH3, you can see it is going from axial to equatorial. That means it is adding. So delta G will be 1.74. It will be positive because it is going to the axial part. Okay. OH also going from equatorial to axial, then it will be positive. Only this part isopropyl will be negative. Why? Because it is going from axial to equatorial. So all this repulsion will not be there. Okay, here you have no repulsion. This is in equatorial. So what will come? You will get this value 0.52. So from the delta G value only you can see this is positive, right? So then this is non-spontaneous. So this one will be much more preferred. But we need to calculate K equilibrium. So let me do that. Delta G equal to minus RT ln K. Delta G is 0.52 minus, so I have told you already, minus R is 0.001987 kilocalorie, and then 298 ln K, then ln K will be minus 0.878, K will be e to the power minus 0.878. So the answer will be 0.415. 0.415. It will be the answer. Okay. Did you understand? Okay, let us move to the next. So it shows that which of the following currently ranks the cycloalkane in order of increasing ring strain per methylene. What I told, that if you have more deviation from ideal sp3 scenario, that will lead to more strain, right? So that is why, see this one, cyclopropane, it is 60 degree, cyclobutane it will be 90, cyclopentane 108, cyclohexane 120. This is much more relaxed. So this one will be the right answer. Now the next one, which of the following describe the most stable conformation of trans 1 isopropyl 3 methyl cyclohexane? So let us just draw it. So I will name it first. Sorry, number it first. 1, 2, 3, 4, 5, and 6. Now 1 isopropyl, I'll give it this one. Okay, but this one I will go on the top of the blend. Then 3 methyl, but in trans. So if it is on the top, it will have to go to the bottom because it is trans. This is your methyl, right? Now you try to draw this in the 3D representation. This is your chair conformation. This is 1, it is on the top, that means it will be like this. Then you have 1, 2, and 3, this position. So as this is on the downside, here will be your methyl group. But is it stable? No, because it will have this 1,3 diaxial interaction with hydrogen. So just flip it. It can flip to the other conformation. So where it will go? It will stay in the equatorial position, and this methyl will go to the top, but there is a competition. So if methyl is there, its 1,3-diaxial will be very less compared to diisopropyl because this group is big. Okay, so stays at equatorial position. So now you see what is which option is correct. So this isopropyl group is equatorial, methyl group is axial. So this one will be correct option. Okay. So this one, name the compound shown below. Anyone wants to try? See, this is top of the plane. This three. This is in the axial. Then you have another one on the equatorial part, right? This is down below the plane. This is equatorial means on the top. So you have another one here, hydrogen. Now you can see it is top. Okay, it is also top. Then what is the relation? Cis, and this is on the adjacent position. This is 1, this is 2. Then cis 1 2 dicyclohexane. Okay, I don't have any response from anyone. Did you understand? Okay, so you can check it later also. I will upload it. So now let me move to some other questions. You have this molecule. So you need to draw it in the 3 dimension. Okay, this is a substituted cyclohexane, and you have the options like this. Can somebody try and let me know which one can be correct? Can somebody try? Okay, I have to complete it. So let me just do it. So I will number it first: 1, 2, 3, 4, 5, and 6. Okay, so now let me do it like this way. So this is 1, this is at the downside. Okay, anyone got any answer? Okay, it's fine. Just a second.
Option B.
Option B. Okay, let me check it. So if I consider this one, 1, 2, 3, 4, 5, and 6. So this is down. This is down. 2 will be also down. That means here 3, 4. 4 will be on the top. But this one will not be stable because there are interaction present. So if we flip it, then down means this one. Then you have also this one down. and this one will be, yeah. Okay, I guess it is matching with the B. This will be the right answer. Okay, so you have to match, okay, both the numbering and the relative, uh, the relation between them, cis or trans. This you have to check it. Okay, and why this is not stable? Because this is big group, so it should be on the equatorial position. So let us move to another question. Sorry. So rule out the wrong constitutional isomer of C5H10. Okay, so you have four options. Okay, you have four options. So you have to rule out the wrong constitutional isomer. So three of them are correct, one is wrong. Can you check it? So you can see here you have hydrogen, 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 hydrogen. So you have C5H10. This one, so 6 plus 4. You have also C5H10. Here how much? 1, 2, so 3 to 5 to 7. So here you don't have. So you got your answer. This one will be right. Just let me check this one also. 3, 1, 1, 2. So 3, 3 is 6 and 4. This is okay. This one will be your answer. And find out most stable conformation of 1 bromo propane. Okay, 1 bromo propane. So this is your molecule, and the option will be. So can you try? I'll give the option. Sorry, option and D will be. Okay, can you try it?
Option C.
Option C. Yeah, this is the right option because uh, you have two big groups, methyl and bromo, that are exactly opposite. So this is called full staggered. This will have the least energy, and that is why it will be much more stable. Okay, then this is kind. Yeah. Okay. So you need to find out the most energetic conformation of cyclohexane, chair, half chair, boat, and tourist boat. Which one will be the right answer? You have seen the energy curve for cyclohexane. It is like this, right? This is your energy. This is some axis, arbitrary axis. This is your chair. What is this one? This is boat. This is twisted boat. This is also twisted boat. This is half chair. So which one is maximum energy? This one, right? Half chair. Okay. Let us move forward. Yes. So you should calculate one more time. So two conformer you have. When it flips, it goes to this conformer. So delta G is 6.4 kilocalorie per mole. You need to calculate the K equilibrium. Okay, and given is T is equal to 27 degrees C or 300 Kelvin, and R is, okay, sorry, this is not kilocalorie, this is kilojoule. Okay, R is 8.3 into 10 to the power minus 3 kilojoule per mole per Kelvin. So you need to answer the K equilibrium value. Can you try it? As we know that delta G is equal to minus RT then K, delta G is 6.4. So here you need to keep in mind the unit. Okay, always. So here it is the same unit, so you don't need to tension. So R is 8.3 into 10 to the power minus 3, 300 Kelvin, then ln K. Ln K will be how much? Check it and then let me know. So 6.4 into this 10 to the power minus 2 will be on the downside, so it will come like this. Then 8.3 into 300. So overall there will be a minus charge, right? So minus 6.4 into 10 by 8.3 into 3. How much it will come? Minus 2.57. Then K is equal to e to the power minus 2.57, right? How much it is coming? 0.076. Okay, so you know that this K equilibrium is proportionate with the product and reactant ratio. So that means 0.076 by 1. So it is almost in the reactive form, reactant form. So this is most stable. And if you need to calculate it, how you will calculate? So, so how much percentage of this one is available? Percentage of R equal to 1 by 1 plus 0.076 into 100 equal to, that is almost equal to 93%. Okay, one is your fraction for the R reactant, and 1 plus 0.076 is the total. Then you take the percentage. You understand, right?
Yes, sir.
So now we go to the next one. Uh, okay. And correct diagonal angle for trans 1 to di sorry dichlorocyclohexane. What will be the dihedral angle between them? Okay, so options are 0, 60, 120, and 180. Can you tell me? Let's draw the structure.
60.
Yeah, it is right. So 1, 2, 3, 4, 5, and 6. 1, 2, 3, 4, 5, and 6. So it is on the top, is here, and it is on the bottom. This here. But I know this is not stable because of the diaxial interactions. Okay, in this conformation. So you have to flip it. So if you flip it, then it will be like this. Okay, now you saw do the Newman projection. So Newman projection will tell you. So just this part I will do. So it will be like, here is carbon, this is hydrogen, here you have Cl, this is carbon, this is hydrogen. So the dihedral angle will be 60. This is the right answer. Okay, so I think I have covered all of the topics for the second week. So if you have any doubts, you can let me know. We can discuss it next week. And one more thing I missed it. So last week, in the last part, there was a confusion, right? For what is that? Yes, methyl radical. Okay, steric number. This was a confusion from the last class, right? So it will be 3, not 4, because steric number always relates to the hybridization. Okay, and in this case, hybridization is sp2, not sp3. Why? Because unpaired electron unpaired electron will unpaired electron doesn't require a hybridized orbital. Okay, so our VSA pair is based on electron pair, because a lone electron or single electron doesn't have that much repelling capacity. So it can stay So the actual structure is like carbon, 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 hydrogen, hydrogen, hydrogen. This is the sp3. So angle is 120, and you have unpaired, unhybridized p orbital. So there this single electron is located. So if you calculate the steric number, will be 3. Hydrogen is sp2. Okay, this was the conclusion from the last class. It will be 3. So okay, with that I close the today's session. Next class we'll meet, and if you have any question, you can let me know. Thank you.
Sir, upload the videos, sir.
Yeah, sure. Today I will upload it.
Last week and this week as early as possible.
Sure, sure, sure. Okay.
Whenever I free, we will read the question answer.
Okay. Thanks.
Okay, thank you.